Okay, let's continue. So in the last class we looked at our differential amplifier, the 5-transistor amplifier, and we looked at its DC operating point and small signal gain. So just to recap, one point we noted was the following: although this fellow was an asymmetric circuit with respect to DC operating point, where I have identical gate to source voltage, or I will say common mode excitation. So although this is asymmetric, for common mode signals, what can you say about the circuit? It becomes symmetric. So which means the drain voltages here, both of them will have to be equal, because otherwise we saw we'll end up with a contradiction. We can easily argue. So which means the currents in both the branches will be equal and be equal to half the current source value I0 by 2. And in particular, can you tell me what kind of biasing is being done for the transistors here? Is it constant voltage or constant current? Constant current. Why? Yeah, of course I have a current source sitting here and trying to bias it at a constant current, right? So which means we saw that. So or you tell me what is defining this source voltage Vx? How will VB determine this voltage? Yeah, again we are biasing with a constant current, and the current that we are biasing the transistor is I0 by 2. If the current is fixed in saturation region, the gate to source voltage is also fixed. So this source voltage Vx is essentially the gate VB minus the VGS we have across the transistor, right? So that's what happens. So which means now tell me, if I increase the bias voltage VB, do you think the current in the transistors will increase or reduce? The question is, if I increase the bias voltage VB, do you think the current in the transistor will increase or will it reduce? It will remain same. Why? Yeah, again it's because we are biasing with a constant current. Again, this is a common point of confusion, making it a nice question for interviews. So a lot of times students might think that, hey, I am increasing the gate voltage, the current will increase. That's not the case. That's why I want you to understand what kind of biasing we are doing for transistors. So here particularly we are biasing with a constant current. So it doesn't matter if you change the gate voltage, the source voltage will adjust automatically to keep the current constant. So that's the point. And then we went ahead to compute the small signal gain. Again, if let us say the circuit was symmetric, to find the small signal gain, what would you have done? You try to decompose the two inputs V1, V2 here as a common mode part and a differential mode part, because if it's symmetric circuits, for common mode and differential mode, circuit simplifies. But because of this asymmetry, we didn't take that approach. Instead, we computed the short circuit GM and Rout, and the short circuit current is essentially GM of this transistor times the differential input. And similarly, we calculated the output resistance separately as up and down resistances. And again, here is where some confusion was there with respect to something. So let's see if you understand it now. So let me consider a scenario like this. I am drawing only for small signals. So let us say now there is a change in the drain voltage by delta V. How much will be the change in the gate voltage here? No change? Is it clear? This is something we discussed in detail in last class. Again, just because I am changing the drain voltage here, it will result in some current, because the current depends on VDS slightly. But just because I have a current flowing here, doesn't mean I'll have a gate voltage generated accordingly. Again, understand the cause and effect. Again, the example I give is turn on the switch, fan rotates, but not the other way around. Okay. So just because I have a drain voltage applied here, the gate will not get set unless you have an explicit feedback. Okay. And again, if you're not comfortable arguing logically like this, we can always solve by KCL, right? So let us say I apply KCL here. This voltage is also VG, or I will not write it. So I have, let us say this is some R. I have current flowing here and down. Sum of these two currents will have to be equal to 0 by KCL. So what is the current flowing through the resistor R? VG by R. Fine. Now let's look at the current through the transistor. For small signals, how do you model the transistor? a voltage controlled current source, and you have an output resistance R0. So what is the value of this current source? Gm times Vg. What is the current flowing through R0? Vg by R0. So sum of this should be equal to, because Kirchhoff told us. So which means, what do you say for, what do you find for Vg? I mean, that's the nice thing about circuits, right? I mean, any circuit given to you, you can always solve using KCL. That's the only thing you need to remember. That's why I always say analog circuits is the most easiest thing to study. As long as you know how to apply KCL and solve equations like this, you can solve in principle any circuit. But that said, then the value you add to the table as a circuit designer is, by not resorting to KCL all the time. Instead, argue from intuition and by inspection and tell what the currents will be and what the voltages will be. Right? That's where your value comes in, because otherwise anyone can solve any circuit by applying KCL and solving linear equations. Right? And that's a skill I want you to develop through this course. Not always resort to KCL, KVL. Try to get some understanding of what's happening by inspection through your intuition. Right? And again, I gave in the last practice problem set, I gave a lot of small signal calculations for you to do. Please work out. And ideally, I would want you to get the result by inspection, right? Argue logically and tell what the output should be. Of course, I'm sure not all the circuits you will be able to solve it like this in the first place. So which means you use KCL, solve it, but don't stop there. You stare at the result and see how you could have arrived at the result by inspection. That's how you build intuition, right? I mean, it's not like, I learned something here, I sleep, the next day I have all intuitions in the world. That doesn't happen. It comes with practice. So you solve the problem, but analytically get the solution, and then look at the solution and stare at it and see why it makes sense, how you could have arrived it, just by inspection. So that's a skill I want you to develop. Right? That again will only come with practice. So anyways, that's digression. So let's continue with our summary. Yeah, so here for the amplifier, here we computed the output resistance. The final output resistance was simply the parallel combination of R0 of M2 and M4. But this doesn't mean that the looking down resistance is R0 of this transistor. In particular, we saw this was actually 2 times R0 of M2. Right? But the final result is nice to remember. So the overall gain was Gm times this R0. And we notice that the gain we get here is 2 times what the gain was with this old circuit. And that we saw that makes sense, because in this circuit we have small signal currents flowing in both the branches, but we are discarding the current flowing in this branch and only using this current for getting the output voltage. Whereas in this circuit, the current flowing in the left side branch is also copied to the right side branch. So both the currents sort of add up. So which means you get twice the transconductance or twice the gain. Great. So now let me actually copy this thing. Let's see if I can. I'll copy it from here. Let me erase this. Sorry. So I'll replace it with a transistor. I'll call this M0, and it is biased with a current of I0. Okay. And I'll apply small signal V1 and small signal V2 here, and this is my V. And just to summarize, what is the small signal gain here of this circuit? Gm of which transistor? M1 or M2? So let us say it's M1 times the output resistance. And what is the output resistance? The final result is simple. It is R0 of the NMOS transistor in parallel with that of the PMOS transistor. So now we have one good candidate for making an opamp. And an opamp is what kind of a controlled source? Voltage controlled? Voltage source. So which means if I say the gain here is A, the output voltage is A times V1 minus V2, obvious. Now let us say go and add a load resistor at the output. Do you think this output will change or will it not change? Why?
It will add in parallel to the resistance of the
I mean,
output resistance.
it is added. Yeah, it is added at the in parallel to the output. But why will the output not change?
Because the output resistance of opamp is 0.
Okay. Or in other words, see what kind of a control source is this? Voltage control. It's a at the output. It's a voltage source. It's a voltage source. It doesn't matter what load you are connecting at the output. It's an ideal voltage source. It will make sure that the voltage is equal to this value, irrespective of what you put there. So even if you go and put a dinosaur here, the output will still be the same for an ideal voltage source. Okay. So now let's try to see. Let's try to add the load to our circuit. So I want to add the load resistor. So do you think can I add the load resistor like this directly and connect it to ground? Can I do it like this? Yes, no? Why not? Yeah, the problem is operating point current. I mean, this resistor will draw some operating point current. So you don't want DC currents to flow. So instead, how do you connect it now? Yeah, that is one way in which we do. So we put a large capacitor so that as we know in steady state, DC current through the capacitor is how much? 0. So no DC current flow, so DC voltage is 0. Now, again, remember we need to have a large capacitor, and on chip having a large capacitor means you will end up occupying large area, okay? Because capacitance is epsilon times A by D, right? So if let us say you want to add a load like this, on chip you don't use a capacitor, so instead we do the following. So now I want to connect this directly without having a capacitor, right? So which means I cannot connect this to ground, right? So what do I do to this end so that no DC current flows? I'll connect this to, what do I connect it to? It's not VB. Yeah, I will connect it to a voltage source. What should be the value of this voltage source? It is equal to the DC operating point of this node potential, correct? If I have a DC voltage source of the same value, I'll say it's V out DC, then no DC current flows. So this is something we may try to do on chip to avoid having large capacitors, right? So you connect the other end of the load to appropriate DC voltage.
You should have access to the
Which one?
to keep
Correct. The idea is most like you want this to be small signal ground, that's all. Right? Yeah. I mean, if let us say you have something where the other end of the load is connected to ground, you don't have an option, you have to use a large capacitor. What I'm saying is this is not always done. If you want to avoid using a large capacitor, then you do this. Is that okay? So now of course tell me, I mean for small signals this is anyway small signal ground. So now with the addition of load RL, how will the gain change here? Or will it not change? What will come in parallel with what?
the output resistance.
Will come in parallel with? It's going to come in parallel with your existing output resistance like this. Is that okay? So which means now with the load resistor, do you think my output voltage will change or will it not change? It will change because your small signal gain depends on RL. So if I change RL, my output voltage will also change. So which means we actually don't have a voltage controlled voltage source, right? Because if it was an voltage source at the output, the output voltage, yeah, would have been rough. It will not change at all, or it will change only slightly, right? So we now have a voltage. Now we don't have a voltage controlled voltage source. Instead, we have a voltage controlled current source. Because for a current source, the current is fixed, and the output voltage will change based on the load, right? That's what we have. So instead of making an operational amplifier or an opamp, what we have at our hand is typically called the operational transconductance amplifier. In short, OTA. Yeah.
If we are using source instead of capacitor, then sometimes it would have a resistance comparable to RL.
Yeah, if that is there, then I mean you can't do this. Assuming that you have a good voltage source, you can do this.
So in practice, both are used, sometimes capacitor and sometimes.
Depends on the application. If the capacitor value is really large, don't do it. But if let us say if you are looking at very high frequency operation, the capacitance value might be reasonably small, so then you can actually use it. So what we have is an OTA. So for opamp the symbol is a triangle. For an OTA you should have a different symbol, and that is a quadrilateral like this. So here the output voltage is not fixed, the output current is fixed. So if I call it V1, V2, so my output current, if I call it I out, my I out will be constant. It will depend on V1 minus V2 times some GM. And of course this output current source, I mean this is essentially a current source now. This will have its own intrinsic output resistance. So I'll call this R out. This is not an additional resistor we are connecting, it is the intrinsic output resistance of the current source itself. Okay. So which means if I were to show, these are the input terminals and this is my output terminal. So what I am saying is this transistor here, this circuit here can be modeled like this as an OTA having some output resistance R out. So now let us say I want to measure this GM of this OTA. I have access to these two input terminals and this output terminal. How will I measure the GM in practice, do you think? I will short circuit this output. So which means all of this current I out will flow through the short circuit and you can measure. And that's what we saw. This is essentially your short circuit GM of this circuit. Is that okay? And again remember, in actual practice, let us say I am trying to measure the short circuit GM here. Will I go and connect it to ground like this to 0 volt, or what will I do? It should be connected to, yeah, it should be connected to the same V out DC, I'll say, because I want this to be a small signal ground, so nothing should change for the DC operating point. So whatever DC potential there it is, you put a voltage source of the same value. So DC operating point does not change, and for small signals this is a short. So often this is called the 5-transistor OTA. Is it clear? Okay, so now yeah, one more thing needs to be figured out. Let me erase all this. Yeah, let's figure out what is the plus and minus sign here, right? And I know this is my output. Let's figure out what is the inverting and non-inverting terminal, and how will you find what is the plus and minus terminal here? How can we find? There is no loop here. Huh? I'm saying this is plus minus, this is my model for the OTA. I want to figure out what is the positive terminal, what is the negative terminal. Okay. Okay, what is the simpler thing I can do? That's all correct.
We can go point by point.
What do you mean by point by point? Huh?
Let's increase the V1.
Yeah. So let us say, in this model here, if let us say I increase the voltage V1, that is the non-inverting terminal, what will happen to the output? Yeah, current will be pumped out in this direction, so the output voltage will. So if I know that if I increase a terminal voltage and the output increases, that is the positive terminal. If it let us say I increase some voltage and this reduces, same thing we'll do here, right? So let us say I increase this voltage here. What do you think will happen to this drain potential? Why?
Common source.
So, I mean, this is all small signal calculations. Remember, right? I'm increasing the small signal gate voltage. So, what will be the? This is the cause. So, what will be the effect of this? Drain current will increase. So, I'm pulling out more and more current from this node. So, if I'm drawing out more and more current, what will happen to this node voltage? That will reduce. So, which means this voltage also reduces. Now, the gate voltage of the PMOS transistor is reducing. What can you say about the current in the transistor? That will increase. So, which means I'll be pushing in more and more current into the output node. What will happen to the output voltage? Is this clear? I mean, that's the same thing like saying that, I mean, for common source, the small signal gain from gate to drain has an inverting sign, right? It's minus GM times whatever, right? And that minus sign comes because of this reason. So yeah, so which means this is going to be my positive terminal, this is my negative terminal, and this is my output. Great. Cool. So now let's do some more calculations on this fellow to get more comfortable with this. See,
Once more, can you explain the current part?
okay, so what I was arguing is this: you increase the gate voltage. So this is small signal increase, right? Small signal gate voltage increases. What happens to the small signal drain current? Increases. So which means I am drawing more and more current from this node. Current flows from drain to source. So which means I am actually pulling out more and more current from this node. So this potential will. That's all. Same thing I am following into. I mean, ideas always there is parasitic capacitance everywhere. So if you are pulling out more and more current, more and more charge is getting depleted, the voltage will reduce. That's the idea.